of ultrasound, you will learn these essentials here. And this is what it's about, Sono basics. Well, what will this talk be about and what is the course about? I've bad news for you. You won't be an expert in performing ultrasound when you went out here. And you won't be an expert on interpreting ultrasound as well. But definitely, after this course, you will have realized the scope of ultrasound. You will understand the image formation in the machine. You will certainly identify anatomical structures. And finally, by end of this talk and by end of this course, you will have the knowledge to approach an ultrasound machine and actually perform ultrasound in a clinical setting. Our agenda for today will be, we will talk about the technique, we will talk about image formation, how is this image generated, and we will talk about the handling of the ultrasound machine as well. I have to say as well, we will talk a little bit about physics, but I will try to do it as vivid as possible. So, let's talk about sound waves, signals, and the image formation. I think you all had vacations, you jumped into a pool, you were swimming around, maybe snorkeling, and somebody jumped just in the pool. And maybe you remember the sound when somebody jumped into the pool. It was something different than when you would stand outside of the pool. And this is about conductivity of sound. And ultrasound imaging is nothing different than what you see there. It's sound waves traveling in water, traveling to cells, and you have all the interfaces, and the interfaces will do the image. This is basically the concept of an ultrasound machine. We have a crystal there. You know this crystal from your fire lighters. When you press down, there will be a spark, and then you will have the flame. We do the same thing the other way around. We give energy in, we have a movement of the crystal, and then there is a sound beam or the sound wave advancing into the tissue. And it looks exactly like this. You see that there is a sanding process where the sound wave is sanded out by the crystal, advancing into the tissue, and you have a clock down there. And basically, ultrasound machines do nothing different than just measuring time. And because we know how fast sound waves travel in water, we can actually calculate how deep a certain structure is when we have an echo. So we talked about echoes. We have a little structure here, and we will send out an ultrasound beam right now. You see the machine is going into sending mode. The ultrasound beam is advancing into the tissue, certainly hitting the structure, and an echo is coming back. And while the echo is coming back, our crystal is in receiving mode again, and we get a signal, and by measuring the time, we can actually differentiate how deep this structure is. And exactly the same works when you have two structures, two different structures. And this is, we have the conductivity differences between different tissues, we have interfaces, and so an echo is generated all the time we hit the structure. The sound wave is advancing into the tissue, hitting the first structure, an echo is coming back, and the sound beam is still advancing, hitting the second structure, and we have a second echo coming back. Let's talk a little bit about frequencies. We have all these different probes. You see on high-end machine here, different probes on the machine. But what are the actual differences in these probes? And it's basically, we have frequencies, very high frequencies, little wavelengths, as you can see in the top crystal. And this crystal is generating a sound beam with a very narrow wavelength. And we can't penetrate in the depths of the tissue. But we have a very good resolution with this kind of beam. The second one is a little bit intermediate. We can't see the really small structures, a little bit bigger structures we can see. And then we have this crystal with this very long wavelength. And as my voice is going deep, it's the same. It's advancing into the deep structures. And what I want to do with you is a little experiment. You know all the basics right now you need to understand an ultrasound machine. And we will build probes right now on our own. I will give you a scenario. We want to look at some vessels at the neck, the carotid artery. And I mean, this is not a very deep structure, it's really shallow. So we need crystals, I would say, with high frequency, not penetrating that deep. And we basically put them all into one row. And you can see, maybe this is familiar for you. This is the linear probe. And it's exactly this. You have a line of crystals with high frequencies, not penetrating that deep. And you have quite a good image. And this is what it looks like. The next scenario. You want to do an abdominal ultrasound, looking for some big vessels, for example, the vena cava. And so, especially if you look into our population in Austria, with all the big belly, you may need some crystals penetrating a little more deep, as you can imagine. And that's exactly what you do. And the other thing you do, you're not lining them up in one line. You want to have them on a round shape, that it is going like this into the body, that you can see also a little more white in the depths. And you might notice that this is familiar for you. This is the abdominal probe, the curved linear probe. Deeper frequencies penetrating more deep, and also spreading of the beam, that you can see a really good wide image in the depths. And this is what it actually looks like if you do an exam. Let's face another scenario. You want to do a cardiac exam. You're feeling the apex, and you want to exactly put down your probe there and have a look on the heart. But you have a little problem. You can't take the linear probe, because you have the ribs, and you have to go through the ribs into the depths, because you can't ultrasound through bones. This is really not the conductivity what ultrasound machines are made for. So we do a little trick. We take one crystal, and we move this crystal around. So we are also spreading the beam in the depths, but we have a really tiny surface area. We have to put down the probe to see the whole heart. And this probe might be familiar for you. The sector probe, cardiac probe it's called, and you can generate exactly what it is made for, the heart beating. So we have talked about the three main probes we have. The linear probe on the left side, high frequency, not penetrating into the depths, on one line, the crystals. Then we have the second one, the abdominal probe, crystals with deeper frequencies to go deep into the body, and also on a line, on a curved linear line, to spread the beam in the depths to see the whole abdomen. And then we have the cardiac probe, also penetrating deep, because you want to go really deep. So low frequency, but with this little trick that we actually wipe around with our beam. When we analyze and want to discuss ultrasound images, we should talk about echogenicity. This is a little term. We want to describe it not like this is a white structure, it's a black structure. It's about echoes. and it's not the color of the tissue you actually look at. So if something is really black, like we have in the middle of this image, some vessels, then it is unechogenic. There's no echo coming out. Then we have areas with a little gray. This is hypoechogenic. Then we have areas which are really bright. We get a lot of echoes, so we have a hypoechogenic structure. And then if we compare two structures with each other and they have almost the same echo, we can call them isoechogenic. Well, let's talk about the machine handling. What it is like if you step up here, go to the machine, and actually want to start them. And for me, it was the same. In the first place, it's a little bit confusing. And if I look on this keyboard, I feel a little bit remembered like this. This is the remote of my TV. And I don't know how you use your TV, but definitely I don't need all these buttons to actually control my TV. And as you might see there, I'm a huge Apple fan. I guess this is a brilliant product. It's everything you need. You don't need all the buttons up there, and you can control everything. And I would recommend for you, think of all these knobs, all these different settings you can set up there, like it's an Apple remote. And I would say there are some buttons. It's a freeze button in the middle. If you see your structure, you have looked, you have scanned all the time for, and now certainly you see this structure, I would push down on the freeze button and say, okay, it's freezed, I have it, I can analyze it. So this is the most important button in the middle. Then I might want to raise the color or the light, so I need the gain to turn it on to get a little bit more bright image. And I should adjust all the time for the depths. These are really the buttons I should have on my thumb on the buttons. And Apple was not that good in doing remotes for ultrasound machines. I would add 2 more buttons. It's the B button for B mode to get this standard image, the brightness mode, the image you have seen already, and also the color flow to get the Doppler effect visualized, that you can see if something is flowing. And if you look right now on this keyboard, I have marked these buttons for you, these 5 knobs you really need. It's not looking anymore this confusing. Let's sum it up. We have talked about knobology. You have the freeze button to stop the image. You have the gain to adjust the brightness of your image. You have the depth to adjust the depth of your image. And you have the beam mode to come back for the normal scanning, and the color flow to actually look at flow. Right now, you can use this machine, but we should talk also about the probe handling. And the probe handling, I would rather say, is kind of important, because this is what you perform the ultrasound on. It's a psychomotoric act, and just in the beginning, it's this psychomotoric act you have to learn, and you will definitely learn it within the next days. And also, you not just have to handle the probe, you also have to analyze the image, and you have to find out, if I see some structures on the left, what is this in the body? Where do I have to move my probe to see it more proper? And you have already learned about cross-sectioning. Everybody who has learned radiology knows cross-sectioning. And it's like a salami, but we are ultrasound, so it's black and white. And it's just slicing up the body and looking at the different slices and analyze them. But you just know CT. And CT is like the swing. It's backward, forward, backward, forward. And the same with MRI, you have the standard planes, it's backward, forward, you can scroll through. But ultrasound is something different. Ultrasound is actually a little more cool. It's really moving in the third space. Yeah? You can move your probe around all the axes. And I will definitely show you right now what it looks like. Maybe you can turn out the lights for me. Well, we have a modified ultrasound probe here, and it's a laser probe. And we will get some fog as well. And you might see right now, can you see it also in the back? This is a beam of an ultrasound machine. Yeah? And I can move it around in the third space, like this astronaut. A little more fog. And that's how you can size up, do your cross-sectioning in the body, and you can move it completely freely. But if you do an ultrasound exam, and let's face one structure, we're cross-sectioning this structure. And it's kind of easy if it's a big balloon, because I will always hit it. It's no problem at all. But it's a little bit different if I have some structures like a vessel, a small, tiny vessel. Right now, I have it in this plane, and right now I would like to see it completely longitudinal. Can you see it all in the audience? Like the ultrasound beam is advancing, and I'm scanning through this vessel. And if I'm trying to get it just moved around, and I'm just moving the probe in all three axes at the same time, it won't work at all. I really have to face, and this is the most important thing you will learn right now, you have to grab your probe really at the bottom, get some skin contact that you don't slide away easily. Control your probe proper, and if you have it in the middle, just turn all the time just in one axis, and you can follow the structure. If you're trying to just move around, you will definitely lose the structure. So all the time, have it in the middle, just move your probe in one plane, and then you can scan it proper. And you can see, I can see the structure actually right now. It's not that easy for me to have this structure in a certain plane. And it's the same if you go to this ultrasound machine and try it on your own to find a structure. And you have to remember all the time, that is what is about probe handling. Moving the plane, that you have a structure in this certain plane you generate with your ultrasound beam. And then just move in one axis with really controlled movements that you can all the time follow the structure and you don't need it. Let me illustrate it again. You have the gallbladder here. And if you move around a little bit, it's a completely different image. Can you see the difference? We see, look all the time on the gallbladder, but we have a completely different image by just panning, tilting, maybe rocking the probe, or rotating the probe. We have a completely different image. And so be careful in the beginning not to move in all axes at the same time, like this astronaut might do, and control your probe proper. Well, let's go to the ultrasound machine. Brilliant. Okay, we have in this box some structures, and you might notice them up there. Is the image freezed? And we have to turn on the gain, I guess. And also adjusting the depths a little bit. And what you see right now is you see a structure, round structure. And I will just grab the probe a little bit for you. And we can scan this structure. And you might notice what it is. From the audience, any guess? What does it look like? No idea? A dolphin, okay, that's interesting. What does it say, make you think about a dolphin? Okay. Let me ask you a little bit different. Is it a flat structure or is it a round structure? I would say you can see this hyper-echogenic line, this bright line. I would say it's round. And you can certainly see also there is something inside. And it looks like little dots. And we flip around. Not that easy to see. It's a tomato. Let's go back. And maybe you can see some patterns you have seen there. It's definitely the round shape of a tomato. And maybe these little points there might be the seeds in the tomato. And just by putting one plane in there, you can already see it might be a tomato. Let's look something different. Any guess what this might be? Is it also round like the tomato? Has it the same round structure? No? Okay. What is it looking like? I would say you can already see the triangular shape. Correct? But definitely by just cutting it in one plane, you can tell what it is like. Maybe you can show us a second plane, and especially Austrians. Yeah? I've already heard the correct answer somewhere there around. So we were first time just cutting it short, and then all the side up. Any guess? The first image might remind you of this image. But definitely by this one image you can tell what it's really like. You need a second plane to actually tell an ultrasound what the structure is. And it was somewhere around there, somebody saying it's an Essiggurkel. Yeah, definitely, it was a cucumber. And you can ultrasound a cucumber there, but you need definitely the two images, the two planes. have another look. Maybe just in short axis. And if you turn around in long axis. Can you understand it? Yeah? Okay, brilliant. Let's go to the next structure. Antipasti. And this is our next image. Okay, you looked before in the box. Definitely, you're correct. But let me show you something more. If you have it in short axis, you just see a round structure with no echo inside. It's looking like a ring. Also, we can't see the bottom. And if you look at a long axis, it's completely weird, isn't it? And what you have to do to really understand the structure is to pan all the way up, all the way down, and you can see there the cross at the end and the hole, the round hole on the other side. Can you see it? So in the first place, we have seen something like this. And it's really difficult to tell this is an olive. And we looked like we did in the cucumber. A second plane, it looked like this. And it's still not feasible to actually tell this is an olive. And what we did, we sliced it up all the way through. Okay, you might tell it's an olive. And if you took in two planes, scanning through the whole volume, you might have this image. And also, you might understand the structure, and you can tell this is definitely an olive. Brilliant. We have talked already about how the ultrasound is generated, how we can get an image from just sound advancing into the tissue, into the body. We have talked about the different probes, the different specifications of a probe. And right now, we also talked about the handling of a probe, that you have to look on all structures, definitely in two planes. And you have to move from one plane, from the short axis to the long axis by just moving in one axis. And then you have to scan all the volume in two planes, and you can tell the structure. But right now, let's talk about what it is like if you as a student go out there and take the ultrasound probe at the bedside and scan a patient. And this is how I would recommend to use ultrasound as a beginner. You might think of the ultrasound as a new stethoscope. You do all the classical physical exams. You auscultate, you palpate, you feel the body, and you might feel there's something going on. And that's when I would take the ultrasound probe and have a look. And it's not the same like I'm sending a patient for a diagnostical ultrasound if something is going on in his liver. I use the ultrasound as a tool to blend it into my physical exam and get more knowledge about my patient, and maybe finding the one or other hint what the best treatment for this patient is like. And we should definitely talk about something else. This is almost the curve of the Dunning-Kruger effect. And the Dunning-Kruger effect describes the relationship between my confidence and actually the wisdom or the experience I have. And you have this first peak. And you might go out of this course and say, okay, I've learned all this cool stuff, and I immediately want to apply it on every patient. And you should definitely not do this. Ultrasound in the first place is easy. It's easy to take a probe, put some gel on, put it on the patient and see an image. This is really easy. But actually, to understand what's going on needs some time. You will learn this by time. It's no question about it. But in the first place, always doubt a little bit your findings. And then there might be the second challenging part, and this is the valley afterwards, when you have done some exams and they were difficult and you couldn't find the right answer. You did it wrong. Don't be inconfident. You will learn over time. So what I definitely recommend to use ultrasound as a beginner is like a tool to include differential diagnosis. All the time, include them, say, okay, this is more likely. Never exclude them, because you might miss it and you did a really wrong thing on this patient. And you will fail. It's normal that you fail. You will learn it by time. So always use the ultrasound to include differential diagnosis in the beginning, not to exclude them. This is the end. This was a brief introduction into basics of ultrasound. I'd like to ask you, are there any questions in the audience right now? Everything is clear? Okay, brilliant. I really cordially wish you the best for the next coming days. Enjoy it. Ultrasound is an awesome method to do better for your patient, to get these more informations the patient needs for his treatment. You can do it everywhere with bedside ultrasound in an inexpensive way and in a not harmful way. And maybe you find something just before a CT is done. Thank you.